Okay, so in very short summary, yesterday we saw how we can access the spin structure for longitudinally polarized photon, so that we have like contributions from the spins of the quarks, which is around 30%. And we also saw how we can access the gluon helicity distribution, either by using inclusive DIS and Q-square evolution, or, and much better, and much better, by using information from proton-proton collisions at RIG, looking at dijets or pion production or others. That's what we saw for the longitudinal spin structure. Then we saw that we can also actually access much more. There are many more different aspects to the spin structure. So there is a difference between longitudinal and transversely polarized spin structure. There are then, once we take into account transverse momentum, we obtain actually the fully accessible we have full access to all the different functions at leading twists. These are 8 functions that tell us about different aspects of the spin structure of the nucleon, looking at correlations between transverse momentum of quarks and the spin of the quarks or the spins of the gluons. So this is where we stayed. And so to access these quark TMD PDFs, we had first data from Jefferson Lab, Compass, Hermes, and now the idea is to improve this, our knowledge a lot by improving the amount of data that we take. So for this, the activities nowadays at Jefferson Lab will be extremely useful because they access the high X region where we have very little constraints, and then the EIC will allow us to extend our kinematic range down to 10⁻⁴. So this is where we arrived. Maybe not such a short summary, but this is where we arrived. So about these TMD PDFs, there is similar landscape, but for gluons. So we can again look at gluons with different polarizations in nucleons with different polarizations. So again, we have unpolarized, longitudinally or transversely polarized nucleons. And there we can look at unpolarized gluons or circularly and linearly polarized gluons. So the gluon is a spin 1 particle. So as we do for photons and their electromagnetic fields, we talk here about circular and linear polarization. The big difference, though, between the quark TMD PDFs and the gluon TMD PDFs is that you have to press on the screen that I can change. Yes, thank you. Is that we basically don't know anything about gluon TMD PDFs. So anything you do there will be extremely useful. And the way that they're accessible, it's, well, the reason why we know less is because the first measurements were done at the fixed target experiments in EP, and there it's harder to access the gluons. And then we could, in principle, also look at PP collisions. But there we saw that we have a problem with factorization for TMDs as soon as we produce additional hadrons. And if we would look at Drelian, well, Drelian is first order sensitive to quarks. So this is why we know so much less about gluons. But now that we'll have the EIC, we hope to improve our knowledge quite a lot by so hadron pairs with high transverse momentum, so back to back, or maybe also looking at particles such as quarkonia can happen. So this was the general picture. Now we can access also gluon TMD PDFs at unpolarized experiments, as we could for quark TMD PDFs, and as we did for quark TMD PDFs, we can only access 2 gluon TMD PDFs, namely for unpolarized gluons in an unpolarized nucleon, and for linearly polarized gluons in an unpolarized nucleon. And the way to do that is by looking at pp collisions and the production of two J psis that are nearly back to back. Now, I know I just said that as soon as we produce hadrons in pp collisions, we have issues with TMD factorization, but there is a nuance to this, namely, if you produce your particles in a color singlet state, then there cannot be any color exchange because they're in a color singlet state, and then factorization works. So this has not been super rigorously proven, but from the ongoing studies, it seems that when you produce two J psis that are back-to-back, factorization seems to, at the moment, work. It's just like the first study, so be always very careful. This can change in the future. So this was for the LHC, for example, what we can do, and then for the EIC, well, as I already said, we can look at hadron pairs or the production of quarkonia, because this one is directly sensitive to the gluon. So at the moment now, studies are ongoing about the feasibility of these processes at the EIC and about how useful they can be or how sensitive they can be to access the different types of gluon distributions. So I will show you one result, namely the one at the only existing one at the moment to have a clean access to gluons, namely at the LHCb experiment. At the LHC, they looked at pairs of J psis that were produced back-to-back, which directly induced by gluons. And if you write out the cross-section, you have contributions from the spin-independent gluon TMD. And then you also get, again, angular modulations, cos2 phi and cos4 phi, which are sensitive to the equivalent of the Burgmüller's TMD PDF that we saw for the quarks. And here you see the result of the measurement. So here you see this phi angle, and here you see, well, the data points and the fit to the data points where the fit is of the form constant plus cosine 2 phi plus cosine 4 phi modulation. And the amplitudes of these modulations for the cosine 2 phi, it is compatible with 0. It's very small. And for the cosine 4 phi, it's close to also compatible with 0. But the hope is to, in the future, reduce the statistical uncertainties and to get better measurements. So at the moment, the signals are very small. And this is basically what we know about the gluon TMD. Okay, so for the future, both for quarks and gluon TMD PDFs. So I was talking all the time about the COMPASS experiment, but COMPASS stopped taking data in 2022. And now, since 2 years, I think, AMBER, the follow-up, started, where AMBER at the moment has not been focusing on hadron structure studies, but they will do soon. So the idea would then to learn actually about the structure of the mesons, which includes then also the spin studies for mesons. There will also be SpinQuest at Fermilab, where there the idea is to really study the U-bar and D-bar Sievers distribution functions. And this is actually the uncertainties that they expect to obtain. And then, as I already mentioned, so at Jefferson Lab, there are ongoing studies, but there are also future studies foreseen, for example, at SOLID. And here you see studies for the Collins asymmetry. And here in red, you see the precision of the expected data points. This to say it's extremely precise. So again, like Jefferson Lab in the high X region will really give us extremely useful data. And then, so at LHC, I was always saying we can do some spin-related studies, but with unpolarized photons. However, there is a project which is called LHC Spin, And the idea is to use the LHCb detector, which is a forward detector. So the collisions take place here, and then the particles produced forward direction are reconstructed. And so the idea is to place a transversely polarized gaseous target at this interaction point here, well, a bit before the official interaction point. And it's really neat. So the idea is to, so at LHCb, you have your photon beams that collide. And now the idea is to then, bit before, have a transversely polarized target and have one of the beams impinging on this target and then detect the produced particles. And to take data at the same time in parallel with the beam-beam collisions and with the beam-target collision. And the huge advantage of using a fixed target is that we can cover then this high X range. So this will give us a complementary channel to what is done at Jefferson Lab. But the beauty is that you there use different collision systems. And again, this high X region is really very poorly constrained, so this will be extremely useful. Now, this thing doesn't build itself like from one day to the other. It's you need a lot of patience. So where we are now is here. And what we have now actually installed there is a gaseous target, but that is not polarized. And it's called SMOG2. And so we can see that, and we take data in parallel, so beam-beam and beam-target collisions. It's really beautiful, like the efficiency for the beam-beam interaction reconstruction doesn't go down. Everything is cleanly separated and reconstructed. It's really beautiful. So we know that that works, but then it's, of course, much more complicated to have a transversely polarized target because you have to have the whole system to polarize your target, and then you also need the system to monitor the polarization state of your target, because otherwise you cannot really do useful measure. So the idea is to first have a transversely polarized target installed somewhere in the LHC tunnel, at the point called IR4, where there's no experiment to build the like small, very rudimentary detector, and then to check if this works. So this will take place from the idea is to install this now and then to take data between 2030 and 2033. And then if everything works well, the idea is then to install the transversely polarized target inside the LHCb experiment and then to take data much later, like after 2035. Okay, so that's the plan. So then we will have for the first time also polarization at the LHC. Now for the EIC, I already said it, we will perform also various measurements. And here, just for completeness, I show you one example for the Sievers distribution functions for quarks. So where we look at unpolarized quarks in a transversely polarized nucleon. So we probe the correlation between the transverse momentum of your quarks and the transverse spin of your nucleon. And you should, the vertical scale, the absolute value has no meaning. What you should look at is the size of the uncertainties. Now we know that the Sievers asymmetry will be very small at low X values, well below 1%. So we have to make sure that our uncertainties, of course, are extremely small. And in these regions here, this seems to work. At higher values of transverse momentum of your produced hadron, this doesn't work as well. At the moment, I have to say that, so what you see here is the total uncertainty, and the little lines are the statistical uncertainty. So at the moment, our systematic uncertainty is estimated in a very conservative way. So hopefully this also will improve in the future. But okay, so from our studies now, we will have, it seems that we will have very, well, we have beautiful data to study all these TMD PDFs. And here you see the impact of the EIC for the determination of the Sievers distribution function. So this is for U quarks in a proton. This is for D quarks. The x-axis is the transverse momentum of your struck quark, and the different ranges here are the different ranges in X. And so the orange is the current uncertainty that we have for the Sievers distribution. and the gray is the uncertainty we expect when we will have the EIC. So you really see a huge improvement for the determination of this T-verse distribution function. Okay, so that was basically everything concerning transverse momentum-dependent parton distribution functions that I wanted to tell you. So the left side of this picture from yesterday. And now the idea is to move over to the right side, so where we will learn something about the distribution of quarks and gluons as a function of their longitudinal momentum fraction and as a function of their transverse position. And to do this, we have to actually access so-called generalized parton distributions. Now, I have to say, everything is more complicated than TMD PDFs. It's more abstract. It's not the TMD PDFs. It's nice because you have this probabilistic interpretation. So you get some intuitive feeling. Even looking at the data I showed, well, it was for the spin-dependent one. No, also for the TMD one, you can really play and you get some intuitive picture. This will all be much harder. So good luck following. So please interrupt if you have questions, okay? Like just stop. It's better we see less than too much and not understood. Okay, so we have these generalized parton distributions. And what these are probability amplitudes, so not probability density. So again, they don't have a probabilistic interpretation. So they're amplitudes, so probability amplitudes to extract a parton with longitudinal momentum fraction x plus psi, and then to absorb a parton with longitudinal momentum fraction x minus psi. And in this process, the proton stays intact, but there is a momentum transfer from the initial to the final state proton. And so there are three variables that the GPDs depend on, in addition to Q-square, again, through Q-square evolution. And the three variables that these GPDs depend on is first the variable x, which is the average longitudinal momentum fraction. Now, the big difference between the PDFs and the GPDs is that when you perform measurements to access PDFs, you use your variable x Bjorken, and you say my x Bjorken variable is this average longitudinal momentum fraction. Here, not, okay? So x Bjorken is not x, but x is the theoretical average longitudinal momentum fraction of your part. Then you see that there is a longitudinal momentum fraction. We go from plus psi to minus psi. So we have a 2 psi longitudinal momentum transfer. And this psi is related to x Bjorken. So if you experimentally access x Bjorken, you are actually, in this case, for the GPDs, accessing this variable psi. And then we have t, which is the form momentum transverse square between the initial and the final state nucleon. And so, as I already said, psi you can access by reconstructing your variable x Bjorken. T you can also access, but the big problem, and that's what makes also GPD so complicated, is that you don't have, in general, a direct access to x. And that makes everything complicated for the extraction. Now, as for the TMD PDFs, also for the GPDs, we have different types of GPDs. And so if you look at the spin 1/2 hadron, so for example, a proton, then we have 4 GPDs where the quarks don't flip their chirality or helicity, and we have 4 GPDs where the quark does flip its helicity. Then we have more subdivisions, namely GPDs that appear when there is no proton spin flip. So these ones we can access easily in unpolarized measurements. Then there is a GPD-E, and there a proton spin flip is involved, so you would use a transversely polarized proton to access this GPD-E in general. Okay, and then the difference between the non-tilde and the tilde is that the non-tilde is for parton spin-independent GPDs, and the one with the tilde is for parton spin-dependent GPDs. interpretation for these ones is a bit more complicated. So, but that's the idea. So again, we have a leading twist. We have 8 GPDs, 8 functions that we try to determine through measurements. Okay. Now, I said these GPDs are complicated, but there are some constraints that we can apply. So we can use some prior knowledge even before doing any measurement on GPDs. If we look at the GPDs in the forward limit, so when there is, if you go to 0 momentum transfer, so this means that T goes to 0 and psi goes to 0. If you do this, then this GPD here reduces to our standard spin-independent PDF, okay? Both for quarks and for gluons. So using this relation, you can already apply some constraints if you want to determine age. In the same way, if we go in the forward limit, this spin-dependent or quark spin-dependent GPD H reduces to our helicity PDFs, okay? And then finally, if we take this one here, where you have helicity flip or chirality flip of your parton, then you, in the forward limit, this GPD reduces to the transversity PDF. And in the forward limit, all these other GPDs here, they just disappear. They're multiplied by a factor, which is sensitive, for example, to the momentum transfer. If it's 0, like 0 times your GPD doesn't appear in your cross-section. Okay, so I already told you yesterday that GPDs are, among others, nice because they give us information about the distribution in the transverse position. So if you take the Fourier transform of your GPDs in a certain limit, then you obtain impact parameter dependent distributions. And these do have a probabilistic interpretation. So these tell you what the probability is to find a quark or a gluon as a function of its longitudinal momentum fraction and as a function of its transverse position. And yesterday I showed that if your nucleon is unpolarized, you get this symmetric distribution, and as soon as you polarize your nucleon, you get a shift in your distribution. And for the unpolarized nucleon at first order, you get this is determined through the GPD H, and then if there is a transversely polarized nucleon, also your GPD E starts to play a role. Again, for people who really concentrate on GPDs, be very careful about this definition of the position because it's a bit more intricate than just the position. It's actually a longitudinal momentum weighted. So this is why also when you interpret these pictures, you have to be a bit careful. Okay, but then these GPDs are also related to the gravitational form factors. And I think this you had lectures about, so you know much more than me about this. And so you learn something about the pressure distribution inside your nucleon and the shear forces. And there have been preliminary studies, or first studies done on this using information that is available. So of course, one has to be always very careful with interpretation. But for example, if you look at the tangential pressure, it would be repulsive for quarks when they're close to the center up to further away, and then it becomes attractive, while for gluons, nearly from the beginning of the center of the nucleon, these have attractive force. So these are games you can play, or games, well, studies you can do. I think it's really nice. Complicated, but really cool. And then finally, also our GPDs are related to the spin of the proton. As we saw, we have the spins of the quarks, we have the spins of the nucleon, of the gluons, and then we have the orbital angular momentum of quarks and gluons. Now, I decided not to discuss this because it's really long and complicated, but you have to know that there are different spin decompositions. There are actually 2 categories. They are linked to each other, but so this is in this decomposition, you do not see the gluon spin appear. It's absorbed into the total angular momentum of the gluon. So this is one decomposition by G. And we already learned that for the quarks, we have a 30% contribution, but we don't know about the orbital angular momentum of the quarks and also not the total angular momentum of the gluon. However, this total angular momentum, both for quarks and for gluons, are related to two GPDs, namely the GPDH, the most well-known, and the GPDE, where you need a transversely polarized target. So it's a really beautiful relation. The only problem is, if you look at it, is that we have to integrate over this variable, the longitudinal momentum fraction, but we cannot access it directly in experiments. So it makes it really complicated. So it's not clear if this relation will effectively ever be, if one can effectively ever use this to really pinpoint down our total angular momentum. There are studies done also with the lattice and so on, but it's really complicated, okay? And in addition, you have to take the limit for t going to 0. So that's the motivation to study GPDs. Now, how can we experimentally access them? Well, the cleanest process is deeply virtual Compton scattering. So where you have a virtual photon that is absorbed by your outgoing quark. The quark then travels, emits a real photon, and returns back to the nucleon, leaving it intact, but with different modes. I say it's the cleanest because we start with a photon and we end with a photon. So nothing non-perturbative. When we perform the measurement, the only thing that is non-perturbative we have to extract from data are these GP. That's why it's the cleanest. And as for TMD PDFs, we need a hard scale in order to have factorization so that when we can really access these GPDs and separate the hard interaction from the soft contributions. And so we obtain again a hard scale through a virtual photon with high virtuality. And so deeply virtual Compton scattering can be accessed by looking at a hard electroproduction of a real photon. So you have again EP interaction, you detect your scattered electron and your produced photon. The recoil proton can or cannot be detected. If it's not detected, because it's an exclusive process, it is your final state is totally determined, you can use these two incoming particles, the electron and the photon, to determine what you would expect for the proton. Actually, what you can do is you can reconstruct the mass of the proton using these particles. If your mass is centered around the proton mass, you know these are good events. Everything that's far away, you know something happened. So maybe this one here dissociated, but you didn't see the dissociation product. So this works well for a fixed target experiment. So these measurements have been performed. So again, at Jefferson Lab, by class experiment, COMPASS, the Hermes experiment, at the HERA accelerator. And then, as I mentioned very briefly yesterday, there is also the H1 and ZEUS collider experiments at the HERA accelerator, so where they collide electrons and protons. Only the electrons are longitudinally polarized. So they also performed the studies of deeply virtual Compton scattering. Now, in addition to looking at the exclusive production of a real photon, we can also look at the exclusive production of mesons, for example, vector mesons, like the rho, the phi, and the omega. Everything stays the same. The only thing is that we have now an additional non-perturbative object that we have to again model from data. Okay, we can't calculate the evolution from quark going to a final state rho, for example. These measurements have been performed at exactly the same experiments. And at the fixed target experiments, you're at lower energy, so you're basically probing quarks. But then at the collider experiments, you're at higher energy and you're accessing smaller X-Bjorken variables regions, and there you're actually basically probing gluons when you study exclusive vector meson products. Now, I told you that we need a hard scale, which can be provided by a high virtuality of your virtual photon, so large 4 momentum squared. But you can actually also learn about GPDs if your photon exchange between the electron and the proton is not virtual, but is a real photon or a quasi-real photon. And then the hard scale needs to be provided though by the final particle that you create. Okay, so for example, you can create a J psi, which consists of a charm anti-charm, or an epsilon, which contains or it consists of a bottom anti-bottom quark. And it's the large mass of these charm and bottom quarks that gives you the hard scale. The difference is that the mass of the charm and bottom quark is fixed. So you perform a measurement at a fixed hard scale. So that's the drawback, if you want. Nevertheless, this process is extremely interesting because, again, quarkonia are directly sensitive to gluons. So it's a very clean probe to access gluons. And again, it's a complementary channel. And this has been studied at the H1 and 2's experiments. And at the collider experiments, what is nice is that you can go down to X Birken of 10 to the -4, as we will also do with EIC, yes.
Why does that channel specifically access gluons and not quarks?
Because you need to get a charm anti-charm quark. So you would, in principle, you could. So you need to form a. So if you would pick up a charm from your nucleon, which is already not easy, you would then have to also create another one. And I think if you make the diagram, this costs a lot of energy. So this must be possible, but in principle, but it's extremely suppressed.
Thank you.
Okay, so then the experiments that have been studying performing measurements related to GPDs are, oh, I don't know why I put this one here, sorry. I know why, sorry, yes, I know why. So we have proton-proton collider experiments. This is half of my talk of today, so I should know. And then we have also the fixed, the EP experiment, so Jefferson Lab, COMPASS, and Hermes, and then the collider H1 and Hera experiment. Okay, so starting with some examples of deeply virtual Compton scattering, so where we produce a final state photon in EP interactions. The point is that there is another process which has exactly the same initial and final state as your DVCS process, namely beta-Heitler. So you can your real photon can come from your initial or your final state electron, but it's not emitted by a quark inside your nucleon. So you're not probing GPDs. Okay? You just have an exchange of a photon between your electron and your nucleon, but you're not probing the quark structure, so to speak. And since you have the same initial and final state for DVCS and beta-Heitler, well, these processes will interfere with each other. So your cross-section will be a contribution from the beta-Heitler amplitude squared, from the DVCS amplitude squared, and then from the interference term itself, where you have the amplitude of DVCS and the beta-Heitler and their conjugate. Now, you can write out or decompose all of these three contributions in different harmonics. And for the beta-Heitler, this is an elastic process, and you can actually calculate it if you know the Dirac and Pauli form factors. Then you have the DVCS, pure DVCS term, which is bilinear in your GPDs, and then you have the interference term, which gives you linear access to your GPD. So that's a nice one. And this is just one example for the decomposition of an unpolarized nucleon and longitudinally polarized lepton beam. You have also compositions if your target is longitudinally or transversely polarized. And analogously to the TMD PDFs, again, some terms appear depending if the electron beam is polarized or not. And what you also see here is that there is a dependence on the beam charge. So you can actually, by performing measurements with beams with charge, you can isolate part of this interference term. And this is exactly what has been done at the Hermes experiment at Hera, because there we had an electron and a positron beam. At Jefferson Lab, there's only an electron beam, and at the EIC, they will only have an electron beam at all. This was one nice advantage of the Hera accelerator. Now, if we, for example, concentrate on this interference term, so you get your angular modulations again, different angular modulations, where the angles are, again, like between your lepton plane and your produced final state particle, and, your lepton plane and the plane formed by your virtual photon and your produced final state particle. So it's a bit the same principle as for the TMD PDF. So depending on the angular modulation that you analyze, you get access to different types of GPDs. Except that, again, it's a bit more complicated. So, for example, if we would concentrate on this C1 coefficient and the S1 coefficient, well, they both give us access to some amplitude called here M11. And this amplitude itself consists of contributions from different Compton form factors. And these Compton form factors are convolutions of your hard scattering, so between your electron and your quark, and your GPDs. Okay? And in this convolution appears this X, but you cannot access it directly. So that makes this extraction of the GPDs very complex. And if you would, for example, perform beam charge asymmetry, so you would get access to the real part of this amplitude here. And so if you do this, then you would actually probe your GPDs as a fixed pointing psi, but integrated over X because of this convolution. Okay? So beam charge asymmetry is like you get one pointing psi, but you integrate your GPDs over X. On the other hand, if you would perform measurements sensitive to the beam helicity, so you would perform beam asymmetry measurements, then you would get access to the imaginary part of this amplitude, and then you would actually probe your GPD at the point where psi or X is equal to plus or minus psi. It's just one point. And this is the full space in X and psi. So here you can just get access to one point. And for beam spin asymmetries and for things like beam charge asymmetry, you integrate over the full range in X. For this, when you get access to your GPDs integrated over X, you can also just perform cross sections or double spin asymmetries. So depending on the observable that you're looking at, you probe this integrated or one point in X and psi. So this again complicates, well, this is why it's so complicated to access these GPDs. Now there have been, I think, as I already said more than once, different pioneering measurements by Jefferson Lab and Hermes. And you see that, well, at Hermes, we could do beam charge asymmetries, then Jefferson Lab and Hermes beam spin asymmetry measurements with transversely polarized target and longitudinally polarized target. So everything has already been done, well, the different combinations, but we need a lot more data, okay? And so here Jefferson Lab has a really nice program for GPDs, and they've been taking data recently with class 12 and will continue to do so. And this is one example of a beam spin or beam helicity measurement, so where you access this amplitude M11 we just looked at. So you have a combination of your Compton form factor H, which contains GPD H, of your Compton form factor H tilde, which contains your GPD H tilde, and you also have a contribution from your Compton form factor E, which contains your GPD E. But the dominant contribution really comes from H, but then you have some suppressed contribution from these Compton form factors. And then on the other hand, you can measure longitudinal target spin asymmetries, and then you get access to a different combinations of Compton form factors, thus of GPDs. And in this case, you actually mainly probe GPDH tilde. But you also have contributions from GPDH, E, and even E. Nevertheless, because of the kinematic prefactors, these contributions are quite suppressed. And by combining these two types of measurements, one expects to have a clean access to GPDH and H tilde. So this is a bit the idea. Yes. Are there any questions about this? Because this is really not very intuitive.
Great. I guess could you maybe I missed this, but could you repeat what the the form factors or convolutions of the GPDs with what other object were they?
The hard scattering. Let me maybe just write it down. Like there will be. I didn't want to put too many formulas, but doesn't always help. So this is your incoming and outgoing photon. This is your incoming and scattered electron, your virtual photon, and your photon, and these are your GPDs. And so what you have in Compton form factors is schematically, you have the integral over your GPD. So integral over X, sorry, over your GPD times this part here, which is your hard scattering part. Schematically, this is the idea. Okay.
Any other questions?
Okay, I'm going to continue a little more because if that's okay, we have a break. You have a break an hour after we start. So I'll do a few minutes more. Is okay? Okay. So because the reason I want to talk a little bit more is because I want to discuss the mirror process of the DVCS process, which is the time lag Compton scattering. So here you don't have an incoming virtual photon, but you have an incoming real or quasi-real photon. On the other hand, you then produce a highly virtual photon. And it's, again, thanks to this that you have your hard scale. And this highly virtual photon then can be reconstructed through its decay into an electron-positron pair or into a mu plus, mu minus. And it's really nice because it's the mirror process. So it allows us to test if the GPDs that we think we access are universal, and then to really understand if we apply all our QCD corrections correctly, so at leading order, next to leading order, etc. So at leading order, this process is supposed to give you the same information as DVCS, but then it's at next to leading order that things start to change a lot. And this has been measured once. And this once was here at Jefferson Lab, so by the class experiment. So they looked at the photon polarization asymmetry, which gives you access to the imaginary part of your Compton form factor H. And then you also can construct a forward-backward asymmetry depending on the direction of your produced lepton. And this gives you access to the real part of H. Now I showed so it's really nice. It gives you like a complementary access to the real part as, for example, we have with the beam charge asymmetry. So this is, I just want to show you it's a beautiful measurement. So hopefully we get more from this in the future.